Welcome back everyone. I'm Dr. Abhinay Anbamani from University of Florida, NFREC Quincy. In the previous session, we learned how to monitor the soil moisture using the light emitting diodes of different colors. We used red for dry, yellow for ideal, and green for wet. Today, we will complete our project by building a fully automated irrigation system that can sense, decide, and act just like a real farm setup. I welcome you all to the session 6, bringing it all together, the smart irrigation system. In this session, we will integrate everything we have learned from sensors, LED, and a motor to simulate an automatic irrigation system. We will connect the soil moisture sensor, LEDs, and the DC motor that works as our water pump. You will see how the Arduino can sense the soil dryness and control a water pump without any manual input. Before we jump into building our automated irrigation circuit, let's take a closer look at the key components that make the system come alive. Each part you see here plays a special role, just like a team working together on a farm. Let's start with the NPN transistor first. The figure 1 shows the NPN transistor. This is a real hero of automation. Think of it as an electronic switch or even a mini gatekeeper. It's going to have 3 different legs, C, B, and E. C stands for collector, C stands for collector, B for base, and E stands for emitter. So, when a small current flows into the base, it allows a much larger current to pass from the collector to the emitter. You can think this like opening a floodgate. In our circuit, the transistor helps the Arduino control the DC motor safely because Arduino itself cannot apply enough current to power this motor. So, we would be in need of a transistor. The transistor steps in as a power bridge. You can think of it like a relay guard. The Arduino sends a gentle signal to the base, and transistor says, "Got it. Let's begin the big motor run." Our next important key component required is the DC motor. DC motor, it represents the water pump in the smart irrigation setup. So when a current flows through it, the motor shaft spins, symbolizing the water being pumped into the field. In Tinkercad, you will see the motor rotate when the transistor allows the current through it. So every time the soil dries out and the sensor value drops, the Arduino tells the transistor, "Hey, open the gate," and water starts running. When the soil is wet again, the signal stops and the transistor will cut the signal, thereby cutting the current, turning the motor off. That's the real world automation. No human switch is needed. Finally, we have the LEDs. Today, we are going to look at an interesting LED called as RGB LED. Inside this, a single bulb are 3 tiny LEDs, red, green, and blue. Each color has its own pin, and by controlling their brightness, we can produce different colors of light. In our case, red means dry, blue means moderate, and green means wet soil. This tiny component helps us see what the soil sensor is feeling. It's like a visual voice for our system. The plant's way of saying, "I'm thirsty, I'm full." So together, all these components, the transistor, the motor, and the LED, form the brain, muscle, and voice for a smart irrigation system. So the Arduino controls the transistor is going to drive the motor. And the RGB LED gives the feedback to the farmer. It's like an elegant teamwork between the electronics and the nature, science and technology in perfect harmony. With this ideology, let's start to design a circuit in Tinkercad. Let's go to tinkercad.com, click sign up, then click create a personal account and try to sign in with Google. By this time, I hope all of you would have been familiarized with the Tinkercad. Click create and circuits. Try giving a name for your circuit, and all these circuits are auto-saved. Now it's time to search our components and bring it to your workspace. The first important component required is the Arduino board. Next, we would be in need of a soil moisture sensor. Next, we would require an RGB LED. This is a new component which we will be learning today. RGB LED, red, cathode, blue, and green. Next, we would require a transistor. There are two different types of transistor, NPN and PNP. We would require NPN transistor. An NPN transistor, you can see it has three different ends: collector, base, and emitter. Then we would require a DC motor. A DC motor has two ends, positive and a negative one. So with this, we have brought all the components onto our workspace. It's time to give the connections. Let's start with the soil moisture sensor. A soil moisture sensor has three ends: VCC, ground, and signal. We are going to connect the signal to the analog inputs. You can take up any of the input signal, and I'm going to choose A0 here. You can connect to any of the analog inputs. The second connection is with regards to the ground. The ground of the soil moisture sensor is connected to the ground of the Arduino board. Next is the VCC of the soil moisture sensor. The VCC of the soil moisture sensor is connected to 5 volt of the Arduino board. With this, the connections of the soil moisture sensor is done. You can give different colors to the wires so that you can understand it better. The ground is always given with a black wire color and the VCC with a red wire color. With this, the soil moisture connections are done. It's time to move on to the LED. We know that every light emitting diode would be in need of a resistor. So we are going to take a resistor for the red, take up another resistor for the blue, and the third resistor for the green. We are going to connect the red to one end of the resistor, blue to the other end of the resistor, and green to the other end of the resistor over here. With this, the anode connections of the LED is done. The cathode should be grounded always, so we are going to connect it to the ground. Ensure the cathode connections are made in black wire color because we're going to have too many connections now and you might get confused. It's time to connect the other end of the resistor to the digital pins. You can connect to any of the digital pin which is there on the Arduino board. I'm going to connect the green to the 10th pin. I'm making the green LED with the wires of green for better understanding. Next is the blue LED. I'm going to connect the blue LED to the 11th pin. With this, the blue and the green LED connections are done. Now it's time to connect the red LED. So let's connect this to the 12th terminal. Again, you can choose any of the digital pins in the Arduino board. Be sure that you are using the same in the code. With this, the basic connections of the LED is done. Now, it's time to connect our transistor and the motor. Our transistor is going to have three different ends: collector, base, and emitter. We would be in need of a resistor to be connected between the base and the digital pin. So connect the base to one end of the resistor, and the other end of the resistor we are going to connect it to 13th pin. Again, the base can be connected to any of the digital pins. As base is going to handle the larger current, it is always better to connect a resistor here. The emitter of the transistor is connected to the terminal 2. The emitter of the transistor is connected to the terminal 2. And terminal 1, we know that it's always grounded. We have the last connection, the connection of the collector of the NPN transistor. The collector should be given 5 volt. With this, all the connections are done. So initially, we have used the soil moisture sensor. A soil moisture sensor has three different ends: VCC, ground, and signal. VCC is given to 5 volt, ground is connected to ground of the Arduino, and signal is connected to A0. You can use any of the analog inputs. Next is all about the LEDs. We have used RGB LED here, and RGB LED has three different ends: red, blue, and green. All the three different LEDs are connected to 10, 11, and 12 of the Arduino board. We need to ensure that we are connecting a resistor between the LEDs and the Arduino board so that safer current is passed to the LED. Next, we have used an NPN transistor and a DC motor. An NPN transistor has three different ends: collector, base, and emitter. The collector is given 5 volt. The base is connected to pin number 13 with the help of a resistor in between. And then we have the emitter. Emitter is connected to the terminal 2 of the DC motor, and the terminal 1 is grounded obviously. So these are the basic connections what we have in our project. Now it's time to code. Please go and click the code option. In code, there are three different edit modes available: blocks, blocks plus text, and text. Click text. Click continue. As I have mentioned already, whenever you bring the Arduino board into your workspace, this default code will come onto your screen. Try erasing this code and you can paste the code which I have. Let's learn the code line by line. Let's start with the first one. Const int motor is equal to 13. So we are going to declare a constant pin assignment for the pump control signal here. You can see that we have connected the pin 13 to the base. So pin 13 will drive the transistor base to switch the DC motor on and off. Next, we have const int red LED, blue and green LED. So we are going to assign 3 RGB LED channels to the digital pin: 12 for red, 11 for blue and 10 for green. So this is the first part of the code, which involves variable declaration. The second part of the code is all about the configuring the setup. So we are going to tell the Arduino board which pins are being used as input and which are being used as output. So pin mode, output. So this indicates or configures the motor control line and each LED channel as the output. So we are declaring the motor, red LED, blue and green LED as the output. We should always remember that the code is case sensitive. So M should be in uppercase letter and P should be in lowercase letter. Next we have serial.begin 9600, indicating that the total baud rate is 9600, means baud rate means the total number of bits which is being transmitted per second. So we are going to open a UART at 9600 bits per second for logging the values. Then we have a delay of 2000. So this optional 2000 millisecond delay, it's like a startup grace period which lets the sensor to settle and the serial monitor to attach. With this, the setup configuration is done. Next comes our loop. This is the third part of the code. So the main control loop is going to run repeatedly. Let's start with the first line. Int value is equal to analog read A0. So what happens here is we are going to sample the soil moisture sensor on the analog pin A0. You can see that the signal is being connected to A0. So we are going to read the value from A0 and store it inside value. Value is a variable name. You can give any name. Then comes float moisture equal to value into 500 divided by 1023. I would like to explain this line now. Let's start with the float. Float is a particular data type. A floating point data type in C++ is used to store a decimal number. We use float here because the moisture sensor calculation involves division that may produce a fractional values. So that's the reason why we use a float here. Next, value into 500 divided by 1023. So what happens here? My ADC holds the value between 0 to 1023. So the maximum raw output is 1023 for 5 volt. So if you want to represent that range as a difference scale, say I want to calibrate the 0 to 1023 in a calibration of 0 to 500. That's the reason why we use this line particularly. Now let's take the sensor value as 0. So 0 multiplied by 500 divided by 1023. This is going to give me an output of 0. Let's imagine my sensor value is 1023. So 1023 multiplied by 500 divided by 1023. So we get the output as 500. So we have mapped the raw ADC range into a calibrated scale. And instead of using 500, you have seen that we have used 500.0, because when we tend to use 500 and 1023 rather than including as a float numbers, these would be treated as integers and the division would use an integer math truncating the results. By writing 500.0, we force the floating point division, giving the precise fractional output. So, altogether, this particular line is going to rescale my analog reading of 0 to 1023 into a calibrated moisture level between 0 to 500 using the floating point math for accuracy. Next, we would like to print all the scaled moisture value to the serial monitor in order to find the live inspection or any calibration. So that's the reason why we write serial.print moisture and serial.println moisture. Yan over here represents next line. Next, we have the digital write. Digital write red LED, blue and green LED. We are going to make all these values as 0 first. Low indicates it's off. We are going to turn all the LEDs off first. So clearing all the LED channels before deciding which single status color to show. So this prevents mixed colors from the previous loop iterations. Now comes our main picture. If the moisture value is less than 220, we are going to assume this as a dry zone. In dry zone, my motor should run. That's the reason why we write motor high. So motor should be on and my red LED should be on. This is all about the dry zone. Imagine we have an optimal zone now. In optimal zone, I still want my motor to be on and my blue LED will be on. That's the reason why we write digital write motor comma high and blue LED comma high. Else, next comes our overwatered zone. So in the overwatered zone, I don't want a motor to run. So I'm going to turn off my motor and my green LED is on. Next, I'm going to give a delay of 500 milliseconds in order to avoid any bouncing. With this, all my connections are done, along with coding. Now it's time to start the simulation. Let's start with the soil moisture sensor. You can see the red LED blinking and the motor is running over here. Imagine I'm going to change the moisture content level. So, at the medium levels, the blue LED lights indicating a moderate moisture and the motor still runs. If the value is going to go beyond 300, you can see here the value till 300 it's an optimal zone, and if the value is more than 300 it comes under overwatered zone. So let me increase the soil moisture content here. You can see the motor has stopped, green LED has turned on, and you can also see in the serial moisture the value is more than 300. So if the value is more than 300, my green LED should turn on and motor should be turned off. So at low values, the red LED is on, motor turns on, dry soil is detected. At the medium value, the blue LED lights and the indicating the moderate moisture. And at high values, the green LED turns on and the motor will stop, indicating the soil is wet. You have now created a complete irrigation model that reacts automatically to the soil conditions. I'm so happy that you have did it along with me. This simulation represents how the precision agriculture works today. Sensors continuously monitor the soil data, Microcontrollers like Arduino make the instant decision, saving water, energy, and time. Automation like this is used in greenhouses, nurseries, and in open field farms worldwide. You have now built the foundation of that particular technology. Congratulations, everyone. You have completed all the 6 sessions of the Strawberry series. From blinking LED to building a full irrigation automation, you have learned how the science and technology unite to make the agriculture smarter. Keep experimenting, keep innovating, and remember, every smart farm begins with a spark of curiosity. See you all in our next learning adventure, and as always, happy learning.